Okay, so next we're going to cover transfer learning, which is how can we transfer knowledge from training on one task and use it in order to speed up training or have a more efficient reinforcement learning agent train on a new task. Usually a similar task, but not necessarily, right? The more similar the tasks are, the easier it is to transfer the knowledge. So when we talk about transfer knowledge, usually we refer to one of the following high-level tasks or high-level approaches, solutions. One would be what's called forward transfer. This is the straightforward approach where we train on one task and then we try to use the knowledge that we gained in order to train the first task in order to have more efficient training of a new task. And here we'll discuss several approaches. We'll start by discussing what happens if we just try it, that is, we just train, use an RL agent to train on the one task, and then just take the same agent, the trained agent, and continue learning on the new task. Next, we're going to discuss fine-tuning approaches, which is how can we pre-train the agent and then just have or defined smaller regions maybe in our network to fine-tune or to make small changes in our model such that the small changes would be able to account for the new task, or maybe allow our agent to quickly adapt to the new task. Then we'll discuss architectures for transfer. Specifically, we'll discuss progressive networks. How do we build them progressively as we move between tasks? And finally, we'll discuss randomization of the source task as a way to generalize the knowledge. So this is forward transfer is the classical knowledge transfer in RL, but of course we have, but we have other types of knowledge transfer that we'll also discuss under this topic. One will be multitask transfer. This is in cases where we train on many tasks and then we transfer the knowledge or try to generalize our knowledge to a new task that is somehow probably related to all of the previous ensemble of tasks. We'll see how we can apply model-based reinforcement learning in for these tasks, for this multitask transfer task. So we'll try to train a model that is relevant to all of the tasks that we train on. And then we'll discuss model distillation. How can we generalize the knowledge over the model that we are training? And finally, modular policy networks, where we mix and match different portions of the policy to address different combinations or different tasks in a known environment, high-level environment, that the tasks may change. We'll discuss that later on. Finally, there is also in transfer learning the idea of multitask meta-learning, where we learn to learn from any tasks. However, we won't discuss this. It's just another type of transfer learning. So let's start with forward transfer. We train on one task and then we try to transfer the knowledge to learn on a new, hopefully similar, mainly similar task. So we'll start with the first solution that we're going to discuss is the fine-tuning solution, and this comes from supervised learning, actually, originally. So what does fine-tuning mean in supervised learning? So let's say we have a task in supervised learning, right, to train a convolutional neural net, and we would like to train it to detect dogs, and we only have 10,000 images that some contain dogs and some don't. Right? These are our labeled training samples. A straightforward solution would be to train the network from scratch using these 10,000 samples. However, convolutional neural nets have a lot of parameters. Usually they're very deep. We saw that. They have several several convolutional layers and several fully connected layers, and just the input dimensionality is very big, right? It's all of the pixels, specifically if you'd like to retain the RGB, the colors in the picture. So we'll have millions of parameters, and usually there's a problem where if we try to train on a small data set. What do I mean small data set? I mean relatively small. That is, that it's much lower than the number of parameters that we're trying to tune. So in this case, right, if we have 10,000 samples and millions of parameters, I can say that it's a relatively small data set, training set. If we try to do that, that usually results in overfitting. Right? Why is that?
Because it gets the network weights get too tuned to this data set specifically and doesn't generalize more?
If you have many parameters, right, more than the number of samples, usually you can have. So do you remember the universal function approximation theorem over the neural net? If you have sufficient number of hidden neurons, you can memorize everything, or you can fully capture any training set, right? Any function, and at the end of the day, trying to fit a training set. This is usually because the hidden neurons, eventually, if you have more hidden neurons than data samples, you get a situation where each hidden neurons can identify one of the samples. It memorizes, right? So it's a bit hand-wavy, but eventually what happens, my claim here is a bit hand-wavy. It's not particularly a specific neuron necessarily, but eventually what happens is that you're able to identify specific samples from your training set, if you have enough hidden neurons. And that's, of course, just overfitting to the training set, right? And we would like to avoid that. But still, this is a common problem. For instance, I do have 10,000 images of dogs, and I would like to train a convolutional neural network to identify dogs. So what we usually do is or the people in supervised learning, they fine-tune on an existing network. Okay, and the existing network can be trained on a large data set of images, right? This is what we're trying to do in this task. So for instance, you take known data sets, for instance, the ImageNet data set, which have 1.2 million labeled images. You train on that. So this data set might have different labels, not necessarily dogs, right? It has other labels that might be related to dogs, like maybe wolves, cats, but maybe not so, like cars and bicycles. But we train on that network with the data that with the labels that it provides. And once it's trained on this dataset, we continue training it, right? For instance, using backpropagation on this smaller new dataset. Why is this helpful? Why might this be helpful? Because a pre-trained model will already have learned features that are relevant to our new classification problem. Now you might say, will it actually learn relevant features? Will it learn what dog ears are or what a dog tail looks like? Not necessarily. It might learn, but it will probably learn more high-level features that are relevant. For instance, what is an eye? What is fur? What are animals' legs? Right? And these high-level features might not be, we might need to learn more high-level features, but those features may be not the most relevant, but still very relevant, and we pre-train them, and they will be very helpful for us to learn the new dog-specific features. Right? That will be substantially faster to train. And they're more general, right? Will suffer less from overfitting.
So here we are assuming that the ImageNet is trained on a data set which would have learned similar features to a dog.
Not necessarily, right? It can also learn
some level, not like cars. It's not trained on
no,
cars.
we can even do cars, right? But then, so for instance, you have a very large data set that learns how to classify cars. And you might say, well, cars have nothing to do with dogs. Well, not exactly. You might have, maybe the more specific features are less relevant, and maybe you need to go more to the basics. But even if you train it on cars, you learn what the sky, trees, I don't know, something maybe in the background, what are circles, what are triangles, I don't know, stuff like that that will eventually, these are some features that are eventually also relevant to learning what, or to identifying dogs. But it's true, if we had a data set that trains on cats and wolves, something that is more related, yes, then it will be more probably, right? There's a lot of hand waving here, that it will probably be more relevant to training on to detect dogs. Nonetheless, right, even if you train images with cars, a lot in the background, maybe around the car is still relevant to, or some geometric features is still relevant for detecting dogs. Okay, so can we take a similar approach and apply it in reinforcement learning? So usually it doesn't work very well. So just taking a pre-trained network and continue training it on a new task using RL. Usually that's more difficult. Why is that? Because RL tasks are more domain specific. It's hard to quantify, but let's just say that RL tasks are very domain specific. They intend to solve a very specific task and only that. So policies or value functions, or both, depending on the algorithm that you're using, they become overly specialized to the very specific problem that you're trying to solve. And that leads to exactly what you said. You know, if I'm trying to identify cars and then dogs, and I'm still telling you that might still be relevant. But if you're trying to train a half cheetah and then as the ant robot, actually they are more apart. They are more different, and it's harder to fine tune between these tasks, although they're in the same environment, in the same Ujuku environment. Another issue that is very specific for RL is that the learned policies, if we train it on a specific initial task, they tend to be of low entropy. That means that they're, out of all of the possible actions, they tend to choose very, very specific actions and not try other actions. And that's very bad when you transfer to a new task, because it leads to loss of exploration. Once we converge, right, on the specific low entropy policy. And so we get the situations where low entropy policies, which are now the starting policy, the initial policy for the next task, adapt very slowly to the new settings, okay, and tend to learn very slowly. And right, if they are very low entropy, in many cases, so you also saw that in your research, right, they tend to collapse and then relearn from scratch the new task.
Negative transfer.
This is known as negative transfer, right, in the literature. Okay, so let's discuss possible solutions to perform successful fine-tuning in reinforcement learning. So, first solution that we can discuss, well, following the low entropy issue that we just discussed in the previous slide, will be to encourage high entropy. And actually this is what we saw in our previous topic with the soft actor critique, and when we defined policy entropy and why it's important. So same goes here for transfer learning. It's even more important to have a high entropy policy. What does it mean to have a high entropy? As we've seen in the previous topic, it means to act as randomly as possible. Of course, we want to have a max-cent objective, which also takes into account the performance, the actual sum of rewards, and the entropy, and we want to maximize some combination of those. Then we get high entropy policies, which lead to more exploration, and more exploration leads to increased adaptability to new tasks. Now, this might sound a bit hand-wavy, and it is, So our TA here is trying actually his research is trying to get into the root of why high entropy policies actually increase adaptability to new tasks. That is, it makes sense intuitively, but what are the mathematical justifications behind this claim? We won't discuss it here though. Just know that it does exist. I know that it sounds a bit hand-wavy, but there is some theory behind it. So as a reminder, this is our maximum entropy objective, which means that we are trying to find the optimal high entropy policy using any max-ent algorithm. Or, as we discussed previously, we can actually adapt any, let's say, many reinforcement learning algorithms that train a soft policy. Of course, we have to train a soft policy. A hard policy will not have an entropy by definition, right? We need a policy that provides us with a distribution over the action space in order to be able to compute an entropy for that. So for instance, we recently saw one such algorithm on the previous slide deck. We saw the soft octet critique algorithm that actually allows us to naturally incorporates, it's defined over the max-ent objective.